Hey, Honors Physics, Mr. Hausman here. We're going to be making the next step into analyzing circuits by leaving series and parallel behind, or at least circuits that have only series resistors and only parallel resistors. Those are kind of straightforward, pretty easy once you get the hang of them. However, real-life circuits that are involved in computer chips and robotics and even small electronic devices, they're usually not purely series or purely parallel. Instead, what they are is something called a compound or combination circuit. So what do you think that might mean? Well, a combination circuit or compound circuit is one that is made of both pathways that have series resistors, like in this animation, you can see in the middle pathway, I3 and I4, the two resistors in the middle, they're series to each other. And I'm referring to, of course, right here. But the whole circuit has a resistor at the beginning, followed by three parallel pathways. So what happens is you have to start using both series and parallel rules, principles, and to analyze pieces of the circuit. And if you can do it in pieces, you can actually pull together a total understanding of the circuit and how the current and the voltage and resistance work together. So we're going to go ahead and review a key idea. That key idea is called equivalent resistance. Now, you've heard me say that. It's just anytime you add resistors, right? But let's take a look at picture A, right here on the left. Well, it's got series and it's got parallel mixed together. This is one continuous pathway that proceeds from italics A through the 8 ohm resistor, through the 4 ohm resistor, and then there's a split in the current. So what you notice right off the bat is that we have a series portion in the front, right here, and we have a parallel portion second. And so what we tend to do is we start to think about that as, can we simplify that? And what I mean by that is we just simply come down here and say, well, I can simplify the first two. I know how to add those. That's just 12 ohms. And notice I turned it into a single resistor of 12 ohms. To get from A to B, that's just a total of 12 ohms of resistance. Whereas 6 and 3, those guys are in parallel. So I go over to my calculator, and I can't show that quite as easily through the video, and I know how to add resistors in parallel. And the formula is, of course, not hard, but just a little bit different. R1 to the negative 1 plus R2 to the negative 1. And then I'm going to take the reciprocal of all of that, because remember, in parallel, it's a sum of inverses. So you'll hear me typing away, and I believe we get, oops, let me try that one more time. There we go. And we should get 2 ohms of resistance. Let me kind of write that out. Let me actually even show it with fractions. Isn't R1 to the negative 1 1 over 6? And R2 is 1 over 3. That's easy to do a common denominator. So what we're really adding is 3/6, but then we have to take the reciprocal of that. So it's 6 over 3, or 2 ohms. So you can do it on your calculator. You can use the sum of inverses, meaning fractions, that way, if you prefer. Most of us are going to just do it on our calculator. Let's keep going. Now, if you ask yourself, what kind of circuit do I have between A and C? Well, that's now a series circuit, because I just have a 12 ohm resistor and a 2 ohm resistor. Those are the equivalents of the previous sections. And so what I can find out pretty easily is that the total resistance from A to C is 14 ohms. And we're going to use that method to simplify complex circuits. And it may not just be simplifying 1 or 2 sections. You might find yourself simplifying many in like a repeated or looping method. But really, the process stays the same. Now, the next key idea, and you're really familiar with this already, you may notice that I'll have built up kind of your skills by doing simpler problems, is now what we're going to do is we're going to review how to use color as a symbol for voltage, because sometimes it's impossible to calculate the current, but we can find the voltage at a given resistor. So what we're going to do is we're going to do color coding of the voltage, but we're also going to simplify resistors. We're going to actually combine what we just did with color coding. So let's start at the top in the very first picture, right up here. And if you could take out your highlighter and you could kind of follow what's going on here, we would say, let's assume, right, since the current is flowing this way, this must be the side with high voltage. So I'm coloring it bright pink, or at least that's the brightest pink we have. Now we're also going to put blue or low voltage down by B, because there's a high potential side and a low potential side. Now what I need to go do, though, is I need to go find a few more colors. We need to go get an orange. So we know that when you go through a resistor, you drop voltage. But here's the kind of the weird part, right? The two resistors here, right, if they're in parallel, we know that they have to drop the same resistance. One of the principles of parallel circuits is that the voltage drop, let's do that in black ink, the delta V across this pathway has to match the delta V here, even though it's different resistors, because in parallel, all resistors in parallel get the same voltage. Going back to color coding, right, it's still the same voltage as long as you don't go through another resistor. So this is the orange, here's the pink, and we've got blue at the end. Maybe that looks purple, but who cares? Now, we go through a single resistor, the 5 ohm resistor in the middle. Well, that means there's another drop. So we could show that there's a delta V, and we could call that delta V3. Maybe this is 1 and 2. And we don't need to worry about quite how much is dropped right now. We will in a minute, but we're going to make that green. And do you see what happens is that you notice now that whatever voltage drop you have after 5, that becomes the remaining voltage has to be going to both the 4 and the 8. So we basically know delta V1, there we go, delta V1 has to be equal to delta V2. We also know that delta V3 is kind of unique all by itself, and we know that delta V4 and delta V5 have to equal each other. Okay? Now, let's combine our skills and talk about, of course, equivalent resistance. So now, the 12 and the 6 are parallel, but I can't really figure out the total unless I simplify those down. So 12 to the negative 1 power, or the reciprocal, plus 6 to the negative 1 power. And we're going to flip that over, and we're going to find out that these two right here, what's the REQ of those? And that is equivalent, if you've done it on a calculator, I did it on the side, is 4 ohms. And then we have a 5 ohm resistor, right? That's still there, 5 ohms. And can we then add the 4 and the 8 that come at the end? So we take the inverse of 4 plus the inverse of 8, flip over the answer, and that's one more resistor, and that's going to be our, oops, let's get rid of that. Sorry, guys. There we go. That's the quickest way to get rid of it. And let's put in the resistance there, 2.67 ohms. 4 plus 8, right? Just want to check, right? 1 over 4 plus 1 over 8. Let's make this a common denominator, 2 over 8. The total of that is 3/8, but we then have to flip that over. So it's 8 over 3, right? 2 and 2/3, 2.67. So we now have simplified a parallel with a 5 in the middle and a 2.67 at the end. And now we can actually just go to the last step. Can I find the equivalent resistance of all 3 of those? If I wanted to say what's equivalent to a 4, a 5, and a 2.67, I just need to add them. And I'm going to find that my resistance is 11.67 ohms. And believe it or not, we can go back to our voltage, and I've been using a highlighter for that. Here's my high voltage, here's my low voltage, And this one resistor, if someone said, can you do analysis of the whole circuit, you would say, sure. From point A to B now, what we have is we have an I of 2 amps. We have an equivalent resistance of 11.67. And so if I wanted to know what is the voltage drop for the whole circuit, for the whole, this equivalent resistance, I would just simply say V equals I times R, 2 times 11.67, 2 times 11.67 is 23.34. So my delta voltage for my entire circuit is 23.34 volts. So that's a kind of a new skill that we're going to be using as we get into level 1, 2, and 3 compound circuits.